Hello, welcome to another module in this massive open online course. So, we are looking at example problems to understand the applications and theory behind the Fourier transform, especially with relevance to its analysis of signals and systems. Alright, so let us continue this, let us look at other problems. So, in this module specifically we are going to look at the Fourier transform of an important signal, that is the Gaussian pulse. We are going to start with that. Okay. So, let us start by looking at the Fourier transform and we are looking at example problems. And more specifically, now let us start a fresh example, example number 12, if I remember correctly. Let me just check it. The previous one was 11. Yes, this is example number 12. So, want to look at the Fourier transform, the ft of a Gaussian pulse. Ft of Gaussian pulse, and by the Gaussian pulse we mean a signal xt which is of the form e raised to minus at square. This is a Gaussian pulse, okay, and this looks as follows: e raised to minus at square. You can see as t tends to both infinity and t tends to minus infinity, this tends to 0, because this is e raised to minus at square and it is a bell shaped curve that looks like this. Okay. So, this is t, this is x of t, the signal, and this is a bell shaped curve, this is a Gaussian pulse. In fact, at t equal to 0, you can see this is e raised to minus 0, the e raised to 0, that is 1, and that is the peak value, and then it decays as t goes to both, that is as t increases from 0 or t decreases from 0 on the negative side, basically it decays to 0, and this has a bell shaped curve. Okay. So, this is a also frequently referred to conveniently as simply a bell shaped. And this is a very important class, belongs to a very important class of signals. It is used in both signal processing, also in communication. For instance, in communication, this Gaussian pulse is used in Gaussian shift keying or Gaussian minimum shift keying, all right, which forms the basis of the GSM, a digital cellular standard, all right. So, this pulse shape is used in the GSM standard. Okay. So, this is termed as Gaussian minimum shift. This is termed as the Gaussian minimum shift keying scheme, GMSK. Okay. So, this is your Gaussian minimum shift keying. Okay. So, this is used in the GSM standard. Okay. Now, the Fourier transform of the Gaussian pulse, that is x of omega, is integral minus infinity to infinity x t, that is e raised to minus t square e raised to minus j omega t dt. Now, there is no straightforward way to derive this. So, what we are going to do is I am going to show you a sort of a different way to derive this, less something that involves a lot more thought than just evaluating the integral in a straightforward fashion. So, first we differentiate this. So, we have d x omega over d omega, that is integral minus infinity to infinity. So, if you differentiate it, now I take the differentiation sign in differentiation inside. So, that is the derivative with respect to minus j omega. So, what that gives me is minus, so e power minus a t square, you can clearly see this does not depend on omega. So, differentiating e raised to minus j omega t, that yields minus j t, differentiating with respect to omega minus j omega t, and the integral with respect to dt. So, which you can now bring outside the negative sign. So, that will be integral that is equal to minus integral minus infinity to infinity j t e raised to minus a t square e raised to minus j omega t dt. Okay. Now, what we are going to do is we are basically going to carry out this integration by parts. So, we are going to use integration by parts. We are going to use integration by parts, and when we use integration by parts, what we obtain is we obtain this. First I am going to integrate this. So, multiply and divide by 2a. So, this is minus j. So, I have to multiply and divide by minus 2a. So, that gives me a plus sign. So, this becomes j over 2a. So, 2a e raised to minus a t square, that becomes in e raised to minus a t square, e raised to minus j omega t evaluated between the limits minus infinity to infinity minus j over 2a. Now, you have to differentiate it. Now, you have to differentiate the other terms. So, e raised to minus a t square, differentiate the other terms with respect to t. So, that gives you minus j omega e raised to minus j omega t dt. So, when you differentiate this with this e raised to minus j omega t with respect to t, what you have is minus j omega e raised to minus j omega t, and the integral with respect to dt is there. Now, if you look at this first term, that is j over 2a e raised to minus a t square e raised to minus j omega t. Now, if you substitute the limits, you can see e raised to minus a t square when t equal to infinity as well as t equal to minus infinity, this is 0. So, this term goes to 0. So, what we are left with, and you can clearly see, and we can bring the j outside. So, minus minus becomes plus, j into j is minus 1. So, this is minus 1 over 2a times, in fact, you can also bring the omega outside, because the omega does not depend on the integration variable of integration, that is t. So, this becomes minus omega over 2a integral minus infinity to infinity, integral minus infinity to infinity e raised to minus a t square e raised to minus j omega t dt, and if you recognize this, this is nothing but x of omega, that is the Fourier transform of e raised to minus a t square. So, what we have shown is we have shown the first step, that is something that is very essential for the rest of the proof, that is the derivative of x of omega dx omega over d omega, this is equal to minus omega over 2a times x of omega. okay, minus omega over 2a times x of omega. Okay. So, that is what we have, that is the first thing that we have, which means this implies that if you take here dx omega, now you treat this as a differential equation, dx omega by x omega equals minus omega by 2a d of omega. Okay. So, from this we are obtaining a differential equation, that is dx omega by x omega equals minus omega over 2a times d omega. So, this is a differential equation. Now, we are going to solve this differential equation. Okay. So, this is basically your differential equation. Now, integrating on both sides, so integrating this on both sides, what we have, so this implies integral 0 to omega dx omega over d omega equals I am sorry, dx omega over x omega equals integral 0 to omega minus omega over 2a d omega. Okay. And therefore, this implies, now this is log natural x of omega evaluated between the limits 0 to omega dx omega or x omega, the integral is log of x omega, and this integral we know minus omega over 2a d omega, the integral of this is minus omega square by 2 into 2a minus omega square over 4a evaluated between the limit 0 to omega, which is minus omega square by 4a, which implies that log x of omega minus log x of 0, that is equal to your minus omega square by 4a, which implies log a minus log b is log a over b, which implies log x of omega divided by x 0 is minus omega square over 4a, and finally, from the original differential equation it follows that x of omega, and this is important, x of omega equals x of 0 into e raised to minus omega square over 4a. Okay. This is basically the next result that you have. So, we have derived except this constant x of omega. So, we have x of omega is x of 0 into e raised to minus omega square over 4a. Now, all that is remaining in this Fourier transform is to evaluate what this constant x of 0 is, which is nothing but the Fourier transform value at omega equal to 0. So, we have to evaluate, so it remains to evaluate, x of 0. Now, recall that x of 0 is the Fourier transform value at 0, which is nothing but, if you look at this, minus infinity to infinity x of t, that is e raised to minus a t square, e raised to minus j omega t, but at omega equal to 0, e raised to minus j omega t is simply 1. So, therefore, this simply reduces to integral e raised to minus a t square dt. Now, this is difficult to evaluate, except what we can do is we can realize something interesting. There are many ways to evaluate this. What we can realize that e raised to minus a t square also represents a Gaussian probability density function, not exactly, but we can consider this with some appropriate scaling to represent a Gaussian probability density function. Okay. So, this you can see I can write this as e raised to minus t square by 2 times 1 over 2a. Okay. And now, if I multiply this by square root of 2 pi 1 over 2a. So, this represents a Gaussian probability density function Gaussian PDF mean equal to with mean equal to 0, okay. Variance is equal to 1 over 2a, okay, because the expression for the Gaussian probability density function with mean 0 and variance sigma square is given as e raised to minus 1 over square root of 2 pi sigma square e raised to minus t square by 2 sigma square. Here you can see sigma square equals 1 over 2a. And we have integral minus infinity over minus infinity to infinity, the Gaussian probability density function, the integral is unity, which implies that integral minus infinity to infinity 1 over square root of 2 pi 1 over 2a e raised to minus t square by 2 into 1 over 2a, or in other words e raised to minus a t square dt is 1. This is the integral of the Gaussian probability density function, which implies, now taking the constant to the other side, integral minus infinity to infinity e raised to minus a t square dt, this is equal to, well, square root 2 pi 1 over 2a equals square root pi over a. This is square root pi over a, and this you can see is nothing but your x of 0. Okay. So, basically that shows us that x of 0 equals square root of x of 0 equals square root of pi over a, okay, and therefore x of omega equals square root of pi over a e raised to minus omega square divided by 4a, and this is the Fourier transform of the Gaussian pulse. Okay. So, substituting, so what we are doing is simply we are substituting the value of, so if we call this as 1, so what we are doing is substituting x 0 in 1. So, this we obtain by substituting x 0 in 1. So, this is square root of pi over a e raised to minus omega square over 4a, and this is the Fourier transform of the Gaussian pulse. So, this is the Fourier transform of the, so the Fourier transform of the Gaussian pulse, remember e raised to minus a t square. The Fourier transform of the Gaussian pulse e raised to minus a t square is square root of pi over a e raised to minus omega square over 4. And as I already told you, the Gaussian pulse is a very important signal that has many applications. So, it's not very straightforward to derive the Fourier transform of the Gaussian pulse. So, it's important to keep this expression in mind. Okay. So, e raised to the signal e raised to minus a t square has a Fourier transform square root of pi over a e raised to minus omega square over 4a. Okay. So, that is the Fourier transform of the Gaussian pulse. Let us now look at the next example, example number 13. We come to now LTI systems, the applicability of the Fourier transform in the analysis of the properties and the behavior of LTI systems. So, consider now we have, so consider the LTI system with the output that given by the linear differential equation or the differential equation, the constant coefficient, what we also call the constant coefficient differential equation dy by dt plus twice yt equal to xt. Okay. So, this is the differential equation, that is the dE that describes the LTI system. Okay. And what we want to do is we want to find the output to a given. So, xt equal to, so again this xt, you can see this is the input and this yt, this is the output. And what we need to do for this LTI, so xt is the input for this LTI system, yt is the output for this LTI system. It is described by this constant coefficient differential equation, and we have to find the expression for the output for a given input signal. Okay. So, that is what we want to do. What we want to do, find the output to given signal xt equals e raised to minus t. So, this is a simple signal e raised to minus t ut. Now, first thing that we can do is we can consider the Fourier transform of the differential equation. So, we need to find the output to the given signal, that is xt equals e raised to minus t ut. So, taking the Fourier transform on both sides, what we have, taking the Fourier transform on both sides, what we have is j omega y omega, because the Fourier transform of the derivative dyt over dt is j omega times y omega. Okay. J omega y omega plus twice y omega, where y omega is Fourier transform of yt equals x omega, which is the Fourier transform of the input xt. This implies that y omega into j omega plus 2 equals x omega, which implies y omega by x omega, which we also call the frequency response of the system, is 1 over j omega by 2, which is also equal to, remember, h omega, the Fourier transform of the impulse response, and this is also known as the frequency response of the system. Okay. This is also known as the frequency response of the LTI system. Now, we have the given signal xt is e raised to minus t ut. We have this signal and we have x of omega equals 1 over j omega plus 1, that is the Fourier transform of x t, which implies that the output y omega to this input is h omega times x omega, which is basically h omega we already know, that is 1 over j omega. We already seen what is h omega. H omega is 1 over j omega plus 2 times 1 over x omega, that is 1 over j omega plus 1, which now I can express this. Now I have to find the inverse Fourier transform of y omega to derive the corresponding signal y t, and now I can use partial fraction expansion to conveniently derive y t. So, I can write this as 1 over j omega plus 1 minus 1 over j omega plus 2, and this is basically the partial fraction expansion. This is the PF expansion, okay, partial fraction expansion, and taking now the inverse Fourier transform, what we have y t equals inverse Fourier transform of 1 over j omega plus 1, that is e power minus t u t, minus the inverse Fourier transform of 1 over j omega plus 2 e raised to minus t u t, which can basically be represented as e raised to minus t minus e raised to minus e raised to minus 2 t u t. That is basically the output signal to the given input. Okay, so, this is your output for the given input, x t equals e raised to minus 2 t, e raised to minus t u t. That is e raised to minus t u t. Okay. So, that is the output to the given input e raised to minus t u t. All right. So, in this module we have seen a couple of other examples of the Fourier transform. First, we have looked at the Fourier transform of the Gaussian pulse, and next we have also looked at the Fourier transform, or how to use the Fourier transform and the frequency response of LTI systems to derive or to deduce the output signal for a given input signal. All right, we will stop here. In the subsequent modules, we will look at other important applications of the Fourier transform, starting with what is known as the Bode plot, to basically get an idea or basically visually, pictorially represent the properties or the frequency response of an LTI system. All right, so we will stop here. Thank you very much.